let's prove that the null space of a matrix is a subspace. What am I talking about? Well, let's suppose A is an n by d matrix. The null space of A is the set of all vectors x where the result of multiplying A by x is the zero vector. And as usual, let's try and make sure we have our shapes straight. If A is n by d, then x would need to be a d by 1, or a vector in Rd, to be able to be multiplied by A, and the output would be a vector with n zeros in it. So these x's are coming from Rd. So the null space is the collection of all vectors that, when you multiply them by A, they get turned into the zero vector, or they get zapped or terminated by this act of multiplying them by A. And now my claim is that this null space is a subspace of Rd. And what I'd like to do is prove, using the definition of a subspace, that the null space is indeed a subspace. What does it mean for a collection of vectors to be a subspace? Well, suppose S is a subspace. What it means for S to be a subspace is two things. One, the zero vector is included, and two, the subspace must be closed under linear combinations. What this means is, suppose U and V are two elements of the subspace, then CU plus DV must also be an element of the subspace. Okay, sometimes this is written as two separate conditions, one being that the subset is closed under scalar multiplication. So if U is in the subspace, multiplying it by any scalar k gives you a vector ku that's also in the subspace. And then closed under addition, that is U plus V is in the subspace as well. But you can combine these into one statement which says that the subspace is closed under linear combinations. So to prove the null space is a subspace, I need to show that the null space satisfies both of these properties. Okay, the first property that it needs to satisfy is that it contains the zero vector. Is the zero vector in the null space? Indeed it is. Why is that? Well, for any matrix A, multiplying it by the zero vector, this is the zero vector in Rd, all this is doing is taking 0 of the first column of A, plus 0 of the second column of A, plus 0 of the third column of A, so on and so forth. This indeed will produce the zero vector as an output. Any matrix times the zero vector is going to give you back a new zero vector. So indeed, 0 is in the null space. Sorry, the zero vector is in the null space. So the first condition is good. What we really need to spend a little bit more time on is verifying that the null space is closed under linear combinations. Let's try and do that. So let me get some space here. Let's suppose U and V are both in the null space of A. And let's suppose C and D are both just arbitrary scalars. What I need to show is that CU plus DV is also in the null space. Well, first, what does it mean for U to be in the null space? What this means is that A times U gives you the zero vector. Okay, and so that means U is a vector in Rd. What does it mean for V to be in the null space? It means A times V is the zero vector. And so now the question is, what happens to CU plus DV? Well, the question really is, what happens to CU plus DV when you multiply it by A? So what is the result of multiplying CU plus DV by A? Well, let's take a look. This can simplify into ACU plus ADV. But now remember, C and D are constants, so I might write this as C times AU plus D times AV. But remember, I know that AU is 0 and AV is 0 also. And so what this allows me to do here is say that this is C times the zero vector plus D times the zero vector. And C times the zero vector is the zero vector, D times the zero vector is also the zero vector, and zero vector plus zero vector is zero vector. What does this say? Well, it says if U is in the null space of A and V is in the null space of A, then any linear combination of U and V is also in the null space of A, because that linear combination of U and V, that's a new vector, and what I've shown is that when I multiply A by that new vector, it also gets zapped into the zero vector. And so what I've shown is that the null space contains the zero vector, that was the first thing I did, and I also showed that the null space is closed under linear combinations. You pluck out any two vectors in the null space and take any linear combination of them, right? I didn't assume anything about C and D, they were just arbitrary scalars. And what that got me back was a new vector, Cu plus dv, that is always also in the null space, given that U and V are in the null space. So what this means is that the null space is indeed a subspace of our D. Good. So now we've proved that the null space is a subspace. Let me give you some context for what it means for the null space to be a subspace in practice. Let's start with the matrix 1, 2, 2, 4, 3, 6. This matrix has a rank of 1, meaning, by the rank nullity theorem, the dimension of its null space is equal to its number of columns, 3, minus its rank 1, which is 2. What this tells us is that its null space is spanned by two linearly independent vectors. Okay? Can we find two linearly independent vectors that live in the null space? Sure. Why don't I call this vector v1, this one v2, and this one v3? Are there linear dependence relationships between them? Yes, because the matrix's rank is 1, which is less than 3, which means two of the columns can be written as linear combinations of just one of them. Okay? Why don't we start by expressing v2 as a scalar multiple of v1? v2 is double v1. Staring right in front of us is an arrangement or a linear combination of the v's that gives us the zero vector. Right? This tells me 2v1 minus v2, and why don't we tack on a 0 v3, is their zero vector. All right, and related, I also know that v3 is 3v1, and following this pattern, that tells me 3v1 plus 0 v2 minus v3 is also the zero vector. What am I getting at here? Well, I found in both of these equations components for vectors in the null space. Here's what I mean. If I look here, what this is telling me is that if I take 2 of the first column of A plus negative 1 of the second plus 0 of the third, I get the zero vector. What that means is if I take A and multiply it by 2, negative 1, and 0, I get the zero vector. What the second one is telling me is that if I take 3 of the first column, none of the second, and negative 1 of the third, I also get back the zero vector. So this is telling me A times 3, 0, negative 1 is also the zero vector. Okay? And these two vectors, to me, not only are they in the null space, but they're linearly independent. There's no way to make 3, 0, negative 1 from 2, negative 1, 0, because this one has a non-zero value in the last component, where this one has a 0. So you can't multiply this vector by anything to get this one. So these two are linearly independent, and because the null space is two-dimensional, any two linearly independent vectors that live in it span all of it, right? Just like any two vectors that don't point in the same direction uniquely define a plane. Same idea. So what this tells us is that the null space is spanned by these two things. So I might say the null space is the span of 2, negative 1, 0, and 3, 0, 1. Okay? And that means this pair of vectors in here form a basis for the null space. What does that mean? Well, and I guess I should say, the fact that we've expressed the null space as the span of some vectors implicitly is using the fact that the null space is a subspace, because one of the big ideas from earlier in the course was that spans are subspaces and subspaces are spans. But what does it practically mean that these are a basis for the null space? Well, what it tells us is that any linear combination of those two vectors will also live in the null space. Okay? And that has some consequences that may not be immediately obvious. Why don't I take, let's just make up some random coefficients, like 3 of the first one minus 5 of the second one. Right? Nothing special about 3 and 5. So I'm just taking a linear combination of this vector and this vector, both of which are in the null space. What that gives me is 6, negative 3, and 0, minus 15, 0, and 5, which gives me negative 9, negative 3, and negative 5. Okay? What is the consequence of all of this? What this is saying is if I multiply a by this thing, I should also get the 0 vector. And maybe I did some math wrong here. Math looks good. If I multiply a by this vector, I should also, no, the math was wrong earlier, and this is how you can tell these videos are not scripted. I'm trying to problem solve with you live here. This was supposed to be a negative sign, so this was supposed to be a negative sign, so this was supposed to be a negative sign here, and this was supposed to be a positive sign. There we go. So now what this is telling me is that if I multiply a by this thing, I should also get the 0 vector. But this doesn't seem, like this seems like a kind of random looking vector. But it's just a linear combination of the two basis vectors we found. Let's verify that, just to wrap up here. If I multiply a by negative 9, negative 3, 5, what that's saying is take negative 9 of the first column, which is going to give me negative 9, negative 18, minus 3 of the next column, so I can get minus 6 here and minus 12 here, plus 5 of the last column. So plus 15 and 30. What do we have here? Negative 9 minus 6 plus 15, and negative 18 minus 12 plus 30. Indeed, that is the 0 vector. Though this is not obviously something in the null space, because just by looking at it, I can't tell that multiplying a by that gives me 0. Indeed it does, because it's a linear combination of the two basis vectors we found. What are they a basis for? They're a basis for the null space of A. Okay, so that's practically what it means for the null space to be a subspace. It means it's closed under linear combinations, and I've kind of just shown you that. I took an arbitrary linear combination of basis vectors in the null space, and that resulting vector, which was this one, also was in the null space, because when I multiplied it by 8, it also got terminated into the 0 vector.